All right, welcome to a tutorial on how to use the electronic CAD features of Fusion 360 to create a circuit board. We're going to be creating a circuit board called the Winky Blink, a really popular project for the grade 8-9 high school level in British Columbia. And this video is being created for the British Columbia Institute of Technology's Technology Teacher Education program, where we're doing a little bit of online learning these days. Okay, so you've got Fusion 360 opened up right here, and you may have seen a couple of my earlier videos talking about some of the jargon that we're going to use in circuit board design and how to play the game flow-free in order to get your brain all set for routing circuit boards. But this is where the rubber meets the road, where the schematic meets the PCB, and we're all set to go here. Now, when you open up Fusion 360 for the first time, you're going to see the mechanical CAD interface. And the mechanical CAD aspects of Fusion 360 are really cool. And what's also really cool is that Fusion 360 allows you to integrate your electronic CAD straight into your mechanical CAD. So when you create a circuit board, you can then come along and design a case to go around it, either sheet metal or possibly 3D printed if that's what you're thinking. Some of the things that you'll see on the screen, typically, toolbar at the top. When you're doing mechanical CAD, of course, looking at the circuit from, or looking at your design from different points of view comes in really handy over here, so you can have your different 3D views. Over here, you're going to see all of your projects that you're working on. Now, I've got a lot more projects showing in here because I've been using it maybe a little bit longer than you have if you're a new user to Fusion 360. You'll see your name up here, and you'll also see your name over here, and this allows you to go in and change some preferences and access your Autodesk account. So big thank you to Autodesk for making this software available for educational use. I'm sure it will pay off in the long run for them. A few other thanks out there. OBS Studio is the software that I'm using to record this video. And BCIT is the institute here in Burnaby, British Columbia that's supporting my time putting this all together. Alrighty, so the first thing we're going to do is we're going to create a new project. And so I've got all my projects listed here, but let's create a new project. And we're going to call it the Winky Blink. So I just clicked on New Project, typed in Winky Blink for the name, and pressed enter. There we go. And it's popping up down here, of course, at the bottom of my list because it's all sorted alphabetically. And I'm going to double click on that. And it takes me into the Winky Blink project. Now, the projects are a really neat aspect of Fusion 360. With it being a cloud-supported program, your projects and your files can be shared with other people through an online environment. This is an advantage over some other versions of software where it can actually be a real pain to share your files because there's many files involved. Nonetheless, we still need to keep close eye on our files. Okay, so now that we've got this set up, we don't want to make a mechanical design. We want to create a new electronics design. So come to the little drop-down menu at the top and go to New Electronics Design and click. And here you go, your window changes a little bit and we have a new untitled window coming up right here. I don't like to leave the windows untitled, so what we're going to do is we're going to save this, and we're going to save this one as Winky Blink Project. And check to make sure that where you're saving it, okay? You're going to have different locations that you can save to. You can think of the locations as being like file folders on your hard drive. So just click on that drop-down menu if you have to, and go up and down there to make sure that you're saving it into the Winky Blink folder. There we go. Now, the Winky Blink project file is what we're going to use to link our Winky Blink schematic file to our Winky Blink printed circuit board file. Anytime you're doing electronic CAD, you're going to have two separate files. One is the schematic, that shows the logical layout of the circuit without worrying about part size or part placement or any of those little details that you actually have to worry about for manufacturing. And the idea of the schematic is to tell the story of how the circuit works. So we're going to be really careful and clear about how we lay that out. Then we're going to use that schematic, once we know we've got a good schematic, to create a printed circuit board or PCB file. And that one is going to be really concerned about all the component sizes and the traces and all the details of actually physically manufacturing a board that accomplishes the ideas that you lay out in the schematic. Alrighty, so let's come in here and you can see that we have a new schematic option right here. Okay, and let's click on New Schematic. And the screen changes again. And over here you can see a new tab has opened up. And right now it says Untitled. And again, we don't want to leave that untitled. Let's save that. Come down to Save. And we're going to call that the Winky Blink Schematic. And again, check to make sure that the location you're saving it is into your Winky Blink project. This goes out on the cloud, bang, saves this file onto the Autodesk website. You have access to it from anywhere you have access to your Autodesk account. So that comes in pretty handy. All right, some of the things that you see on the screen right here, your toolbar along the top right here, don't go clicking on things there just yet. We're going to go through some of the most important ones in order. Down this side, you'll see a list of all the parts that are going to be added to your project. We haven't added anything yet, so it's pretty empty right now. And over on the right side of the screen, you've got some filters over here so that you can hide and see different things on your circuit if you're looking for something. Those are going to be more useful when you get to more complex circuits later on. I think we can see everything we need for the Winky Blink on one screen without having to filter things out. Okay, this is good. We've got our project open and we've got our schematic saved. We've got nothing in the schematic. It's time to add some parts. Let's start by coming up here to the Add Part function. When you click on Add Part, a new window will pop up right here and it will show you all the parts that are available in the system. Now the parts are stored in libraries, and parts are really important because they link the schematic symbol, the idea of the part, to the footprint, the physical implementation of the part. So just as you've got a schematic design and a printed circuit board design, you need to have the schematic symbol and the actual footprint, the physical representation of the project in there as well. So any of these, you can click on a drop-down menu. And so when you're looking for capacitors, you'll see them all listed together in different sections here. And keep in mind, there are millions and millions of electronic components out there, about 100 of which we're going to use regularly in high school electronics. So part of the trick is finding which components do we want and which libraries have the most useful parts for us. A lot of the libraries that come with Fusion 360 are designed for more heavy-duty or industrial use or advanced research type things, not necessarily for your grade 8 and 9 students or even your grade 11 and 12s, let alone post-secondary students who are just having their first introduction to electronic CAD. So what we're going to do is we're going to add some libraries that are maybe a bit more optimal for the parts that we're looking for. And to do that, we're going to come to Open Library Manager. The Library Manager pops up right in here. And just as if you're programming an Arduino, libraries can extend what you can do. In Fusion 360 Electronic CAD, we've got a whole bunch of libraries available for us to use that have been created by people who know that we need more. Now, we didn't have any in our design and we didn't have any in use right now, but if you come over to the ones that are available, you'll see that there are literally hundreds, possibly thousands, I haven't counted, of different libraries available for you to use. And each of them has different parts in it, and each of the parts will have a different footprint if it's manufactured in different sizes. So for instance, you might have an Atmega 328 chip that's produced in a surface mount footprint or one that's manufactured in a through-hole footprint. So you'll have one part, same schematic, but different physical implementations of it. It can get complex quickly, but the libraries help us keep track of that. All right, so what we're going to do now is we're going to add a couple of useful libraries for making the Winky Blink. So if you come down to search for library name and click right here, the first one we're going to look for is the Adafruit Library. There we go. You don't even have to type it all in. Just start typing ADA right down here, and it should automatically find the Adafruit library. And as you'll no doubt be familiar, Adafruit has been a real leader in the development of open source electronics, so big shout out to Adafruit for making this very cool and useful library available. Click on it and hit Use. All right, bang, that disappears from the ones that are available. And if we come over here to In Use, there we go. We've got Adafruit available for us to use. Fusion 360's gone online, downloaded all the parts, and stored them locally on our hard drive. Let's come back to the available ones, and we're going to look for the battery library. So just type in BATT, and you'll see that there's a number of different battery libraries out there. And we're just going to go for the first one that pops up here because I've already gone through and looked at them, and this one has the part that I want. Okay, so just go ahead and under battery, click Use. Okay, this is great. We now have the Adafruit library and the battery library available for us to use. None of them are being used in our design yet. We're about to change that. So we can close this window. And there's our libraries available for us right here. And now it's going to be time to add a part. Now you have to be a little bit careful when you go to add parts, because if you add the wrong part, you're going to have to go back and change it later on. And thankfully in CAD, making changes isn't that hard, but it's sure a lot more efficient to get it right the first time. The first part that we're going to add is the battery. And so click on the drop down for the battery library. And as you can see, there's a whole bunch of batteries available. Now, click on one of the batteries. And when you do that, you should see the schematic symbol for the battery pop up over here and the footprint, the physical representation of the battery pop up over here. This doesn't look like a 9-volt battery to me, and we want a 9-volt battery for our schematic. Now, one of the ways to find the part that you want is to click on the first one in the list and then hit the down arrow. And as you hit the down arrow, you'll just start cycling through all of the different batteries in there. You'll see that there's actually a recording on how popular some of the parts are. And you'll go through here and you'll say, that's not a 9-volt battery. What a lot of these are, all different ways to put batteries onto your board. So coin cell batteries, lithium batteries, very neat options for creating cool projects. If you see red pads like that, now for most of the stuff you're going to make in the high school shop, red pads are a warning. Stay away from the red pads. They're actually really useful in industry. They're surface mount pads, and you can certainly design homemade boards and high school shop made boards using surface mount components, but we're not doing that right now. We'll come back to that later on in a future lesson. Here's something that looks about right to us. If I take a look at this, we've got the battery schematic right here. And this is going to give us 2 holes on our printed circuit board where we can plug in a 9-volt battery. A couple of things that you'll see down here is information on the battery and how it's being used. That'll come in useful later on when we're looking for the correct size capacitor and thing like that to put on our board. So when you select a part, always be careful to check the schematic, the footprint, and any additional information about dimensions that are included in this window right down here. Go ahead and click OK. And now you've got a battery and you can put it on your screen somewhere. How exciting is that? Now, you'll notice the battery is sitting there horizontally. If we want to rotate it upwards, You can click right on there and zoom in a little bit. Standard practice on a schematic is if you can make the positive voltage go upwards, that's great. So I'm just going to zoom back out here. I'd already checked to make sure that the positive voltage is going upwards. And I'm going to put that right there. And then I'm going to click OK. We now have a battery on our circuit board. What's really cool is that later on, when we transition to the printed circuit board view, that battery is not going to show up looking like a schematic of a battery. It's going to show up looking like the footprint of the battery. That will give us the correct dimensions for building our printed circuit board. Okay, now let's add the next part, the resistors. So we can come in here to add part, and we don't want to add a battery. So we can close this off right here. We want to take a look in the Adafruit library. And oh my goodness, there's a lot of stuff in the Adafruit library. Well, you can scroll down in the Adafruit library and RGB. Here we go. Now, it wouldn't be so easy if they add resistor on it, but this is R-US, meaning that they're using the American symbols for resistors. And again, there's a whole bunch of different ways that you can install resistors. So for instance, when you look at this footprint right here, you can see that this resistor has been installed vertically and the lead's kind of been bent right over so that it goes straight back down in your board. And that's a good way to install a standard 1/4 watt resistor like we'd use in the shop, but use very little space to do it. Only thing is it makes it a little tall, maybe easier to be bumped or damaged, so we probably won't use that one. And you can see that the reference right on there has a V for vertical. Here's something. So we've got a resistor right here, and the symbol looks like a resistor value. Footprint, that's what our resistors look like when we put them on a board. That's all looking good. Quick thing to check though is that the grid right here, the spacing is 5 millimeters. Now, 5 millimeters is a little bit small unless you've got a really tiny resistor. I think we can probably go with a little bigger spacing for our resistors. So you can see right here, we've got /5/7. That's starting to look a bit more like our resistor setup. Oh, there's a vertical one. There's a vertical one, a little taller. There's a slightly bigger resistor. Okay, and let's come down here. This one is going to be on the 9 millimeter spacing, which is probably going to work nicely in our printed circuit board. We can always come back and change that to a different physical footprint later on, but pick the 0207/9 that we have right here. Okay, and let's add that to our diagram for now. All right, now again, we're going to want to rotate this resistor. And if you've got this schematic for your Winky Blink open in front of you, there's 4 resistors that go into the diagram. And let's put one right here, one right here, one right here, and one right there. Then you can click OK. Now, in the event that you got the resistor into some space that you didn't want to, you can come down here and you can click on this. You have a move function right up here, and you can click on that resistor and you can move it around and you can get them lined up, and then you can click OK. Keeping the resistors lined up is a really good idea because, again, the schematic is designed to be neat and tidy. The schematic is the story of how your circuit's going to work, and people have to be able to read that schematic. So we've got those components in there. We'll come back and we'll give them values later on. Let's go to the next component. We want to add some LEDs. After all, what would a Winky Blink be without a little bit of blink? So come to your library and go to the add part function again. And no, we don't want resistors. We want some LEDs. Well, there's a whole bunch of different LEDs that you could access, and the Adafruit library is really huge. And as much fun as it is to go through and look at every possible component, wouldn't it be nice if we could just search for some LEDs on here? Come down to the bottom, and in the search attribute, just type in LED. Press enter. That goes through all the different libraries that are on your computer and finds anything that has the word LED either in the name or the description of the part. Now, many of those parts will be surface mounts. We, again, want to use through-hole parts for this project, so we can turn off surface mount device. And let's just do that search again. And there we go. I just came down here, and to redo that search, I turned off SMDs, clicked on there, and hit enter and redid the search with the surface mount devices turned off. And what do we see on here? Well, we've got some drop downs, and we can click on here, and that looks like a typical LED. We've got the correct symbol right here. That looks like a standard footprint. Now we do want to check to make sure that the size is correct. And as I come to this window here and scroll down, this is a 3mm LED. And you'll notice in the name LED 3mm. To get our footprint correct, we want to use a 5mm LED. That's the standard size of LED that we use in a lot of our projects. If you want to go really tiny and you have access to 3mm LEDs, go for it. But we're going to use 5mm LEDs right here. This looks like parts that we've used before. Click OK. And there we go. We're going to put 2 LEDs into our project, and they kind of go just in parallel with the high value resistors R3 and R4. Okay, we've got LEDs in our circuit. Now, one of the really important parts of our circuit is the transistor, because the transistor functions as a switch that turns the LEDs on and off. And so, guess what? We're adding a part. And this time, let's type in transistor and do a search. Now, in my shop, we like to use a transistor called the 3904, or the 2N3904. It's an NPN transistor. Thankfully, the 2N222 is very much the same part. Now, a lot of transistors will look exactly the same. So all the bipolar junction transistors that we use, BJTs, as opposed to MOSFETs, have a particular type of chemistry and design inside the transistor that makes them work. So a 2222 and a 3904 in a circuit like this are going to function very close to identically. And when you look at the top, you'll see this familiar transistor package with the emitter, the base, and the collector. And the emitter, the base, and the collector will be mapped out on here and should be correctly mapped to each one of these pins. Something to note is that the name of the package that we're using for this transistor is the TO92. All right, so here we go. We're going to hook this up, and Adafruit's been really good right in here. They've given it nice big oval pads so that when you drill it out and solder it together, it should go together fairly easily. There are other designs for an NPN transistor, and you can take a look and find them in different libraries. But some of them will put the base pin further back here and use round pads, which just gives you a little bit more space for soldering. Sometimes makes it a bit more difficult to route and insert the part. This looks like a great part. Okay. 2 transistors. One of them is going to come down right over here in line with this LED. Give yourself a bit of space. And the other one's going to come over here. But before we put it in, what we want to do, just to make it look pretty and keep everything organized and make it easy to run our nets later on, we're going to mirror it. So it comes down right in here. Now, we don't want to do any mirroring when we're making our printed circuit board. When you mirror something in your printed circuit board, you're going to run into a problem because it flips it from one side of the circuit board to the other. You're messing with a physical part. In schematics, because we're just talking about the idea of the transistor and not worrying about its actual physical size or anything like that, we can mirror away on these parts to our heart's content. Okay, now we're going to add the capacitors. And again, just as we searched for transistor, let's come in here and we'll take a look for capacitors. You can probably get away with just typing in CAP. All right, we've got the Adafruit library up here, as well as the libraries that came installed with Fusion 360. And let's go with the C-Paul. Now, we're using an aluminum electrolytic capacitor, which is a polarized capacitor. In other words, you have to put it in the right way around, or else it might explode on you. So click on the C-Pole, and as you go through this list, you'll see that some of these, oh, there's one that looks kind of like our capacitors do when we put them on the board. Nice vertical implementation right there. So let's just take a look and see if this is going to make sense. We've got the correct schematic symbol. We've got a footprint that looks like it makes sense, and they even give us a size right in here, and it says that it's about 5 millimeters. Okay, 6 millimeters it says right down here. Note that part right down there. 6 millimeters in diameter. For a 10 microfarad capacitor like we're going to use in this circuit, that's a pretty standard size. The grid that it refers to right here is the spacing between the holes. 2.54 millimeters is 0.1 of an inch. And, well, somehow inches got involved in circuit board design long before certain countries standardized on the metric system. So anyways, 2.54 millimeters, not 2.5. Perfectly fine. Let's go ahead, add this capacitor. Okay, and the capacitor needs to be rotated a little so that it lines up nicely. And we'll pop one in right here. And then you can either mirror it or rotate it twice and put it in right here, because one capacitor points in one direction and the other one in the other. There's our components for making the Winky Blink. We're going to add one last thing just as a safety and security check, and so that you've got an excuse to talk about diodes with your students, we're going to add the diode. Again, come up here, type in diode. All right, there's many different types of diodes that you can add, and the Adafruit library has access to many. The 1N4004 is pretty common. A lot of the diodes that we've got in the shop are sometimes a little bit bigger than that. I'm just looking at the spacing right there, and the grid is 10 millimeters. Yeah, 10 millimeters is 1 centimeter. Diameter 2.54. Those look like appropriate dimensions for the diodes that we're going to use. If you've got any doubts, you can take a diode off of an existing board that you have and just use your vernier calipers and take a measurement off of that. But this should be a great diode to add to our board, the 1N4004. Okay, and again, we need to rotate that into position. Don't put it in this way. That's pointing upwards. We want it pointing downwards. Again, we're setting it up so that electricity is positive at the top of the board and then kind of flows down this way before returning over to our battery over here. We now have all the components for our board. It's time to start hooking them up and building the nets that are going to build our board. Now, I'm a little bit compressed on this screen, and I keep having to zoom in and out, and that's probably a little bit frustrating. We can get around that by coming over here, and right here where you've got all your projects showing, we can just close that data panel off, and now we've got more space on the screen over here. If you ever want that back, click on the little grid right there for Show Data Panel, and it comes back. But for right now, click on Close Data Panel, and there we go. We've got a little bit more space to work now, and you can probably see this screen more easily. Okay, so to hook things together, we join them together with nets. And a net is a continuous copper connection, or a part of the printed circuit board that's going to be at the same voltage. And later on, we'll talk about all the different cool things we can do with nets. We can provide different classes for the nets, so you can have power and signal so that you make bigger copper traces for your power lines versus your signal lines. We can control how they bend around the corners, all sorts of neat stuff that you can do. But for right now, just come to the end of your battery and come across to the resistor, and then come from the resistor over to the next resistor. And now we have one common net. And this net will be given a name, and it'll be some inscrutable computery type name, but hey, we've got a net on there. And let's connect a couple more nets. Now, anytime a net joins at a corner right here where you've got three pieces come together, you should see a dot form. Okay, if you don't see that dot form at an intersection, then you might have something going on. Sometimes you have to click to make it go around a corner. You have to force it to turn that corner. And let's see, we're going to come down right here. And the LED right here is going to come down, and it's going to connect to the positive side of a capacitor. So this LED comes down and it connects to the positive side of that capacitor. And one of the cool things that we can do with nets in schematics is that we can jump over top of other lines. So right here, I can just come down right here and take the bottom of that resistor and take it over to the base of the transistor. Now that works out really cool in a schematic, but my goodness, would that be a problem on a printed circuit board, because now we'd have two nets touching each other, making them the same net, because we'd have two pieces of copper touching right there. We don't want that. In the schematic, we're fine though, because this is the idea of the board, not the physical implementation of the board. Okay, so that's come through there, and you'll notice we do not have a dot right here. That means those are not connected. If I saw a dot there, that would be a problem because they would be in the same net. Alrighty, so we've got that hooked up right there. Let's take this one down, and again, we're going to jump right over that line, which we can do because we're in the schematic, and we're going to connect it right there. And let's finish hooking up this board. Take the collector, bring it up there, so now the electricity can flow down through the LED, through the transistor, join our emitters together, join them into the diode, and take the diode, bring it back to the battery. And the last thing we have to do is join the capacitor in to the circuit right here, and join the capacitor in to the circuit right there. Whoops, that doesn't look right. I didn't want that. Okay, if you end up making a mistake, don't panic. It's CAD. Control Z. Control Z. If only I had a Control Z for life. All right, let's take that and connect it to the, oh, I'm not getting it to pop up again. Remember, you have to tell it what you want to do. We want to make a net. Come up here, make your net, and come across to right there. Take a moment to double check your schematic design. You may have a printout of the schematic design sitting in front of you right now. Take a look at it. This is all good. And this would be a good time to save this design. So just come up here to File and click on Save. And it's going to ask for a version description. User saved works just fine. If you'd accomplish something momentous, you could say, yay, I'm all ready. It doesn't matter what you put in there too much. You'll notice though that up here in the tab, it did update your Winky Blink schematic to version 2. It keeps track of each version that you've made. In the event that you make some catastrophic error, you can go back to a previous version. Yeah, you've got all sorts of options. You can come in here and you can move things around. So if you click on the move, you can move the battery in right here, bring it in a little closer. You might have to move a corner in to bring it like that. And various things you can do to make your circuit board look, or make your schematic look a little bit neater. Now, one of the things that's really important that we have to be able to do, let me stop moving things around, I'll just click on OK, is we have to add some values. Okay, so under the Modify tab right here, we can add a value. And let's start by adding a value to our resistor. So our new value for R2 is going to be about 470 ohms. And since it's kind of hard to find the ohms key on your keyboard, you could just say 470R. Do the same for R1, 470R. Nothing magical about the value of 470. It's just a fairly standard resistor that will throttle the amount of current flowing through the LED right here. Down here, we're going to make these a 56K resistor. If you want it to blink more slowly, use a higher value, sorry. And if you want it to blink more rapidly, use a lower value right here. You don't have to use the same value on both sides, but just for standardization, we'll make both of them 56K resistors. For your capacitors, our standard value is a 10 microfarad capacitor, which we'll represent as 10U. For this capacitor right here, 10U. Okay. Our transistors are already labeled. They say that they're a 2N2222, which is perfectly fine because we can drop in 3904 to replace that. And our diode down here is a 1N4004. Any standard power diode is going to fit right in there, standard rectifier diode. It's going to work just great in that application. And AB9V for our 9-volt battery. Okay, things are looking really good. We've got names, we've got part numbers. As we do this, you can see that we're building up a parts list over here, and we've got the values of all the different parts that are coming in here. And you can take that list and paste it into a spreadsheet or into a Word document. So when you're telling students how to build this circuit, you've got all your parts labeled and ready to go right there. In fact, if you were going to have students build this circuit by hand, you're now at the point where you could just take a screenshot of the screen and put that onto a handout, and you could deliver it to them and say, go ahead, make the circuit. We want to go a step further though. One of the things that we want to do is we want to tidy the schematic up a little bit, document it a bit better, make it look a little bit nicer. So for instance, right now you'll notice that all of the labeling is vertical or not right next to the part that it's referring to. Let's see if we can rotate it around so it's a little bit easier to read. Again, the whole purpose of a schematic is to communicate to a human in a way that a human can understand how things are hooked together and how to put the circuit together. And we can make that easier by coming up here and selecting the rotate button. And for C1, you got to get right over top of that little crosshair, and we can rotate that into a vertical position. And we can do the same for the 10U. We're going to come back and move that later on, but let's just go and find, whoops, I rotated that too many times. There we go. Make that 10U. Again, too much clicking on there. Come down to our diode 1. Make that nice horizontal and easy to read. Our part number, we'll sort all that out later on. Just anything that's vertical, come along here and use your rotate function to turn it horizontal so it's easy for us to read. I think I've got everything there. You can just click OK. Now we can move things so that they're nicely aligned. You might have to zoom in a little bit. You can roll your mouse key and click on the crosshair, and you can use the crosshair to put R2 and 470 R right next to the resistor. R1, not right there, somewhere right in there, right in there. LED 1 should not be written over top of any of the lines. Okay, so just as you'd know from mechanical drafting, don't put your text, don't put your labels over top of any of the lines that are showing anything important on there. Yeah, you just want to, we're not going to get too fussy about standards on here, but we want it to be easily legible and make it look somewhat professional here. There we go. There's alignments that you can do on that. C1, we can put right there. A little bit of spacing, probably better if we do it C1 and 10U right there. C2. Woo, didn't mean to zoom in that much. Holding down your center mouse button allows you to pan the drawing. Rolling the center mouse button allows you to zoom in on the drawing. So pick a zoom scale that works for you. And let's align things here. That one's not wanting to snap to the grid nicely. Let's see if we put it over on that side and then move C2 over there. Ooh, can't put that on top of that line. There's ways that you can finely adjust them, but that'll do for now. And then our battery. Now that we've got the symbols and text all lined up on here, we'd like to add a little title to this. And to do that, we come to the Document menu. And under the Document menu, you'll see the text icon. Pops up right here. Type in something suitable for your title block. Winky Blink. Who made it? J. Brett. And the date, March 2020. Okay, and maybe click on the alignment in the middle right here, and then you can drag your cursor over here to see how big that's going to be. We probably want to make that just a little bit bigger. Let's go up to about a 0.07. There we go, and put it in a suitable part of your document. And click OK. There we go. You've now got a schematic right on here. It's all ready to go. Let's save it before anything goes wrong. Okay, so again, come up to File and Save, and User Saved, and your Winky schematic is updated on there, and now you see it's changed over to V3 because it automatically keeps track of things as we go. Oh, don't like where my AB9V is. Come back to Design, move that up to over here. I think something happened while I was doing a little bit of video editing there. Okay, so we're good to carry on here. We've got a schematic made. We've got it saved. It looks good. One of the interesting things is that, just turn off my print function there, is that if you want to print a paper printout of this, the software in Fusion 360 is actually an integration of a pre-existing software package called Eagle that Autodesk bought from a company called CADsoft, and they haven't integrated all the buttons into the standard Fusion 360 format just yet. This is still a fairly new package as of March 2020. So what you actually have to do is you come to this command bar in the top where you have access to Eagle's command line interface, which goes back decades, and you just type in print up there, and all of a sudden a print dialog box comes in right here, and you can go and send this out to your printer. We don't have to do that right now, but there you go. If you want a printed copy for your records, that's how you get the printed copy. You actually type print into this menu right up at the top. Okay, so that's really cool. We've got our schematic all done, and it's ready to go. Let's make a printed circuit board. So we've got the Winky Blink schematic open here. Remember I said we had a project? Now we've got a window showing the schematic in our project window, and the Winky Blink project includes the Winky Blink schematic. And by clicking, we had to click on this tab to get back over here. That was what I did. Nothing too fancy right there. Click on the Winky Blink project that we saved earlier. And now we're going to click on this button right here for New PCB. Fusion 360 takes a second and it thinks about it. And bang, there we go. We've got a slightly different looking window that's popped up right here. And again, it's called Untitled. We don't like to leave it named Untitled for too long. So come over here to File, and let's save this as Winky Blink PCB, because this is the circuit board. And now we've saved it on there. Off to the side is where all of your components are. And you'll notice that rather than appearing as schematic symbols, these are the physical representations of your project. So what do we do with them? Let's draw a box around them, highlight them all, and then move them into the middle of our printed circuit board. Whoops. Careful what happens when you press and hold that button to zoom in too tightly. If you ever lose all of that, you've got your grid settings and your zoom to fit button right down here. So that's going to make it easier to see what's going on. Now it's time to start arranging some of these parts. Now, one of the things that confuses a lot of people when they start going from a schematic to a PCB is the concept of these air wires. And these little wires that are showing in yellow right here represent the nets. Now you'll recall in the schematic when we connected two parts together, they were joined with something called a net. Well, this line right here also represents the net. And we want to arrange some of these parts. You can see that there's a list of nets over here, net 4, net 6, net 8. We want to arrange these parts so that we can route the nets. In other words, turn those air wires into physical copper traces as easily as possible. So let's start sorting some of this out. And to do that, we want to move some things around. So click on Move, and you've got to click right on the crosshairs, but let's bring our battery right over to here. So this is where we're going to solder our 9-volt battery terminal clips right onto the board. And then we're going to come to R1 and R2. So let's get this capacitor out of the way for now. Okay, and we can move the LED out of the way for now and just let those lines keep crossing each other. We're going to sort them out later on. And let's bring our 470 ohm resistor right here, right in there, and another 470 right there. The 56s will come down here. Now you kind of have to play around with this, and it takes some practice before you'll get the hang of moving things around. The resistors, when I lay out this board, I tend to follow what I've done on the schematic. For simple boards, that usually works. So I'm going to do some rotating here before I do anything else. So I'm just going to click OK on my moves, and I'm going to click on the rotate button instead. And there we go. Oh, rotated it too many times. I want it standing up like that, like that, like that. Make my resistors nice and vertical. Okay. Then I'm going to move them into place. Didn't want to move that number just yet. I just wanted to move the resistor. Okay, so don't worry about anything else right now. Just focus on your battery right here. We're going to have our positive red lead from the 9-volt battery clip come into the board right here. And then we're going to have a copper trace that connects the two 470 ohm resistors because those are all on the same net. Nice, easy. The 470 ohm resistor comes to a 56k ohm resistor, both R1 to R4 and R2 to R3. Our LED is going to come over here, and our other LED is going to come in here somewhere. Okay, and if we take a look at that, you can see that this air wire actually comes over to this side. So let's rotate these so that their cathode is facing downwards on our screen. Again, we're sort of following the schematic concept of having the electricity come in the top and flow to the bottom, if you refer to positive as being the direction of flow. And here we go. We're going to move this. Let's pick up move. And for right now, I'm just going to pop that in right there. Pop that in right there. You know, have a little bit of symmetry. The diode is actually only going to connect over here, so we can pop that off to the side for right now. And our transistors, oh, I got a little warning beep. You may have gotten them already because I didn't click on the crosshair. You have to click right on that crosshair to move the transistors or move any of the parts where you want to move them to. And let's bring these capacitors back up into the middle right here. As you can see, as we start to move things around, we start to declutter some of the air wires, and we get them to not cross each other. It's not a crime if they do cross each other, it just means we have to be a little bit more clever about our routing. Let's carry on in here and let's do some rotations so that we can rotate this, and now you'll see we've got fewer air wires crossing each other. That's generally a good thing. Let's move that right over to here in line with that resistor. And let's move this one right over to here. You'll notice as we move it around that the air wires will jump, okay? And they will jump to the nearest place that they need to be connected to. And that's okay. Remember, they're just a concept. They're an idea that you need to connect this to this with a piece of copper. It doesn't have to go in a straight line. It could come up and underneath here and around here. It just is one piece of copper that can't cross over any other pieces of copper. Okay, let's rotate our transistors so that our emitters are coming out on the bottom. Okay, so looking at that, there we go. And let's rotate this one a couple of times. And, oh, pardon me. There we go. So looking at that transistor, we go, looking at it from the front, we go emitter, base, collector, and our emitters are coming out here and going to the diode. And we'll also rotate that diode around so it's in a nice vertical orientation over there. And we'll click OK. And we'll do some more moves. Get that diode in there, nice and vertical. Get those two transistors lined up, not because of any electrical reason, mainly aesthetics. There's no reason that you shouldn't aim to create a compact, tidy circuit board. Okay. Now, I may have gone a little bit fast. I have made a Winky Blink before, and you may still be beating your head against the wall, trying to get this to all line up. And if that's the case, that's okay. Just take a moment and work your way through the interface until you have something that looks like this. That's why you've got the pause button. You've probably used it on me several times already. Okay, when you've got to the point where these are all arranged in a sensible way, what you're going to do is you're going to save this. So just come over to Save, File, Save. There we go. Now if you need to go back to that at any point, you can go back to it. There's a couple of things we need to do in order to make this board work for us. One of the things that we need to do to make the board work for us is we have to tell it some of the parameters that we're working under. And if you're making a board in a standard high school shop or you're making a board at home, chances are you're going to be making a single-sided circuit board where the copper is on the back and the devices are on the top. And so we need to tell Fusion 360 that that's what we're going to be doing. So to do that, you have to come to the rules DRC/ERC. That stands for Design Rule Check and Error Rule Check. And as with anything electronics, there's lots of rules. We have to tell it what the rules for our board are going to be. So click on DRC. When you click on DRC, the Design Rule Check rules will pop up here. In the Fusion 360 design rules, we can specify this for our board. And we're going to go through each of these tabs and talk a little bit about what they mean so that you can set up your board to be exactly what you need it to be for your purposes. The first thing that we're going to do is we're going to take a look at the layers. So when you click on the Layers tab right here, you can see a little graphical design of what's happening with your board. You've got copper on the top, copper on the bottom, and fiberglass in between. And this gives you the thickness of each layer, and that's perfectly fine. Now, Fusion 360 can handle up to 16 different layers, and in commercial circuit board manufacture, they're able to do that by sandwiching different layers together. So you can have multiple layers of copper wedged into your board, which is how very complex boards like your cell phone or computer are able to be manufactured. We're not going to get that fancy. We only want one layer of copper on the bottom of our board, and we don't need to use the vias, the plated through holes that come down and connect the top of the board to the bottom of the board. To change this into a single layer board, come down to Setup, and where it says 1 and 16, meaning that you've got layer 1 and 16, so you can see right here as you click on that, it provides some more definition on what's going on. We're just going to change this to say 16. Okay, and as I do that, you'll notice that the vias disappear and the copper disappears from the top layer. Oh, I didn't mean to hit enter right away. Sorry, let's go back to design rule check. There's a few other things that I wanted to take a look at in here. So layers, we set to 16. Okay, now clearance is something else that we can set on here. There's a whole bunch of different clearances that you can set. And this depends on your manufacturing tolerances. Fusion 360 is set up for commercial work and uses parameters that commercial board shops would have no problem handling. However, we're going to have to increase this a little bit wider, and I like to have at least 10 thousandths of an inch clearance between everything on the board. So you can come through here and just everything right in here, you can just change it to 10. As we do that, you can see it shows you over here what dimensions you're changing. So here, it's the distance between a pad and a wire. And let's make sure we've got at least 10. And here, it's between a pad and a pad. Let's make sure we've got at least 10 mil, or 10 thousandths of an inch. And since we're not using vias, we don't have to worry about the vias. Okay. We're not using surface mount devices. That's what SMD stands for. And we're not going to worry about the same signals part for now, just so long as it knows to give you 10 thousandths of an inch space between your pads. Let's take a look at distance. Okay, and the distance between the objects and signal layers, it's got copper and dimension right here. 40 mils of spacing is probably fine, okay? Let's take a look at our sizes. This is the thickness of the traces, the copper traces that we are going to route onto the board. And again, 6 mil, 6/1000ths of an inch can be handled really easily by commercial fab plants. I know if you're good with toner transfer, you can get down to 10 mil or 10/1000ths of an inch. For our purposes, we're aiming this to be a successful project at the grade 8, 9 type level. Let's set the minimum width of our traces up to 25/1000ths of an inch. Okay, and just click apply right on there. The annular rings. So this is the distance right here that our pads are going to have. So what this does is this is a percentage of your hole diameter. So when you brought a part in, the part would have said how big each of the leads was on that part so that your board design would know how big a hole to drill for each part. And this is saying it should be 25% larger, but this also allows you to set a minimum distance right here so that you've always got enough copper there in case a student is off in their drilling or off in their soldering, or they don't etch just perfectly. Let's take this and let's increase both the minimum to 15 and the maximum to 25 so that the pads will be a little bit bigger on our board. Now you might actually see that do something right here because we've just increased that minimum diameter. If I click apply, watch some of these pads on the board. And oh, I guess they were all up to size. Let's just try changing our percentage right here. Let's take that up to 35 now and apply that. And looks like we had some nice big pads on there to begin with. Okay. Shapes are for surface mount devices. The pads will follow what we have in the library. We can play around with them a little bit, but let's leave them as they are in the library. Supply, this is just for thermal isolation, not stuff we have to worry about it. And masks, again, this is something that you'd worry about if you're dealing with a commercial manufacturer. And very miscellaneous things that your design role check is going to do. Anyways, once we've set all these, click apply, and you can close the window right here. That's great. Now we can go back to designing our board. So come back to the design tab. You get this window pop up right here. And what we're going to do now is we're going to route our boards. We're going to do manual routing right here. And so click on route manual and just drag that window off to the side. And there we go. Bang. We've made a connection right there. And unfortunately, you'll see it's red. Remember I said red is bad? It's actually good if you're doing surface mount devices and working on a top layer. But let's just undo that. You can hit Control Z or click on undo. And let's tell it that we want it on the bottom layer, please. So here we go. And let's route from there to there. And it comes up in beautiful blue, not ugly red. Watch out for those red lines if you're making a single-sided circuit board. Okay, so now what we're actually doing is we're looking down at your printed circuit board from the top, and it's like you've got X-ray vision. You can see the diodes sitting on the top, and then picture your monitor as the circuit board, and these blue lines are actually on the back of the monitor. They're the lines on the copper layer at the back of the board. We can go on. And as we do that, we keep making connections. So rewarding to hear it go bling, although bling often means there's an error. Now you'll notice I'm doing all the easy ones first. And what do I mean by easy? I mean the ones that don't cross anybody else. Oh, here's a nice one. We can put a chamfered corner in right there. Come right across there. It's beautiful right there. And now we've got some that are getting a bit trickier because they cross right here. Now, this one needs to go from here over to here. We can't come down this way and cross across here because we'd end up crossing this air wire and our nets would run into each other and they'd join together and there would be much sadness in our circuit board. So we're going to come to right here. We're going to run underneath that resistor, come down here, and zigzag across our board like so. Now, this one says this needs to be connected to right here. And again, you're probably looking at that saying, uh-oh, I'm trapped. There's no way out right there. But remember that this pad is already connected to this pad right here. So if we take this line right here, bring it right up there. See how that air wire jumped right up there and it says, oh yeah, you can connect here. And that's all connected. And when we look in here, it says net 4, and everything on here is labeled net 4. Everything over here is labeled net 9, and everything in here is net 8. We can change the names of the nets later on. That's a very useful thing to do when you have more complex boards. But by doing a couple clever things like that, that makes that a little easier to do. And now we've just got this corner right in here. Remember how I was saying it was good to play flow free? You ever played flow free or flow free with bridges? It's an app you can get for your phone. You can play it online. And it's basically a game where you try to connect dots without crossing the lines. We have to connect some dots without crossing the lines, and sometimes you need to think a little bit outside the box. You need to come up with a solution that says, what's going to be the easiest way to make these connections? Well, if that one comes down to right there, that's going to block off and completely encircle anything right here. Now, if I had a bigger capacitor, I could route it right up underneath there. But I think there's a better solution. Let's make this connection right over to here. Now that leaves this connection. We need to get this one connected to right here. Well, remember, it doesn't necessarily have to come from right here because this is connected right here, and we can go underneath other objects. If we could go underneath the capacitor, bit of a tight fit. If we could go underneath the LED, again, with the level of manufacturing we have in the high school shop, probably don't want to do that. But we can definitely go underneath a resistor and route it around this way. Start routing here. Bring it up and around. And now all of those air wires are gone, replaced by copper traces that don't cross each other. So our nets are not shorting out to each other. They're all connected. Now, one of the neat things when you get to this stage, for those of you who like to make neat, tidy little circuit boards, is you can click OK on our manual routing, and you can come in here and you can use your move function, and you can start saying, well, can I make this smaller or more compact to save board space? Now there comes a certain point where the answer is yes, you can, but don't waste your time. This is going to be made by grade 8s, and you can make your life miserable by making it too hard for them. But at the same time, it's neat to see what you can do because you can move things in, and so long as they don't overlap with each other, you can make things quite a bit smaller. We'll leave that right there. You can also move the paths right there. Let's go in here and make sure we click. Oh, where's the transistor's crosshair? Right there. There we go. Now I'm moving that transistor And I can bring the transistor in up from the bottom right there without making it too hard to manufacture. I can move that one up a little bit, and I can move that one up a little bit. Now right here you can see I'm getting a little bit close on there, so maybe I come in here and straighten that back out again, like so. If you want to get really fancy and play around, you can even come in and you can look at the corners, and you can change how the corners are set up so that they're chamfered and things like that. We're not going to worry about that for right now. Okay, we've got a lot of this stuff in place. And right now, we've got everything sorted out into layers. So I'm going to stop moving things around. I'm just going to click OK. And if you come up to the layers right in here, we can display our layers. Okay. And we can choose which layers we want to see. So if I only want to see the bottom layer, I can click on bottom. Well, bottom's already showing. I guess we need to hide everything. So we've got all our layers selected. And let's just come down here and highlight all of our layers. So everything's all selected, and just go hide layers. Bang, we can't see anything now. So if we want to see something, let's turn on the bottom layer, and we can see the bottom layer. And the bottom layer is our bottom copper layer. And that's part of what's going to be etched onto the board. But along with that, you're also going to have those pads. So let's show that layer. And now you can see the connection between the pads and the bottom layer. And this is what you're actually going to etch onto your circuit board. So if you wanted to make that board right now, you could come up to the, click OK down here, as it reminds me. And you could come up here and in the command line, type in print. And there you would have your board coming out right there. And make sure that when you print it directly out onto a printer with a scale factor of 1. Always check your sizes after you do a print, particularly the first time you're using a new printer. Sometimes you do have to worry about mirroring things. We're not going to mirror that, okay, because it's already on the back side of the board. So when you think about how that's going to transfer onto the board, it's going to transfer on there just fine. We're not going to rotate it or make it upside down, but you should check all black to make sure it comes out black and solid. We want it to be nice and solid right on there. And if you don't want the little caption at the bottom of the page, you can turn that off. It doesn't really matter. Okay, so you can go ahead and print that out, but don't do it just yet because we can make this better. Let's cancel that. Let's come back here. We've got our layers turned off. We want to turn them back on again. So let's come to display and we'll go to layer sets down here. And let's go to preset standard and click show layers. There we go. And now we've got all of our standard layers showing. So this is a neat way to be able to see just the parts of your drawing that you want to do. All right. Things we could do to make this better. Remember in the schematic, we rotated and moved the names and values of some of our parts around here. Well, let's rotate everything so it's easily readable. The 9 volt stays right there. LED 2, transistor 1, transistor 2. LED 1, R3, R4. Let's just move them around so that they're a little easier for whoever's assembling our board to make. Let's them follow our instructions because every symbol that we use down here is going to match up to all of the symbols in our schematic. Now the nice thing is that because this would, if we decide to print out onto the top side of the board, you don't have to worry about whether those are over top of a copper line or not, because that copper line is on the bottom side of the board, and anything that prints out here will be on the top side of the board, and you'll have a very opaque board in between there on the way. So you could put that right there in the interest of us having lots of space and making it easy to read when everything's on there. Oh, right down there looks like a wonderful spot. This is particularly useful if you want to print out just a picture of the overall board for somebody to know how to design it. And that looks a little bit nicer. Now the other thing we want to do, click on OK to let it know that you're done moving things, is we want to be able to mount the board onto some form of case or device, and usually to do that we need to put a hole in it. So we want to place a hole on here, and in order to do that, it doesn't show up in the main place menu. You have to click on the little drop down right here, and then you come down to hole, and it just gives you a little logo, symbol like this, and you can see the size of the hole. Now, if you're manufacturing the board commercially, this is a great thing to do because it tells the manufacturer where you want that drill hole to go. If you're making it on your own shop though, that's not going to show up in a useful way for you. So I'm assuming you're making this at home or in the shop, so we're going to cancel that. And what we're going to do instead is we're going to come to the Document tab right up here. And in the Document tab, we're going to draw a circle. And we're going to make sure that we have the bottom layer selected. This means that we're going to draw the circle in copper, so it will etch right onto the board. So you can come in here and draw a circle about right there, and draw a circle down here, down here, down here. We may be overdoing it with four drill holes on there, but you can get them nice and aligned. And should you use this design to create a part, 3D printed part as a case, you should be able to align those holes nicely and get your alignments to match up. So we'll just click OK right on there. Alrighty, now the other thing we want to take a look at is the size of the board. And for that, we need to zoom out just a little bit. Remember when we started, we had this big gray background and little white area that we're working in right here. Come to the edge and click on the edge, and you can just drag that edge right in here. Right up nice and close to where you had those holes. And now this is going to tell you how big your board is. It's telling us that while we're doing it. You can see the information just off to the right of the screen there. It says board information, width 2.29 inches, 2290 mil, 2290 thousandths of an inch, and height 1900. So this is about a 2-inch by 2-inch board. That's pretty big for a Winky Blink, but hey, it's our first one. Maybe you can move things around and shrink it down to a little smaller size. Alrighty, the final thing that we're going to do is we're going to put our name on it because we're pretty proud that we made it, and we're going to put that name on the copper layer so that that name sticks on it and shows up on the copper layer. And so what we're going to do is we're going to draw just like we did before, but the text doesn't show up in this main menu. We need to click on the down arrow, and then we need to click on text and enter your text over here. And we'll just say Winky Blink J Brett March 2020. And then just play with that size down there. I think that might be a little too big. And let's see if we can tuck that in somewhere. Drop it down to 32. And since we're putting this on the copper layer, we can't have it overlay with any other copper. Now, since it is annotation, if we wanted, we could rotate it, and make it a little bit larger. But this will fit in right there fairly nicely, and we can say OK. Now, you'll see that it's got this all crossed off. That's just so that nothing else is routed in there. And there it is on the bottom copper layer. I know the text looks like it's crossed out right here, but when it comes time to print this out, that cross-hatching is going to disappear and you'll just be left with the text inside of there. That is put in there mostly as a reminder not to route anything else through that area. So the board looks pretty good right now. And this is a fairly simple board, and we've intentionally made it to not have any errors in it. There's a useful tool to find errors if we do have them. You'll remember that earlier we used the design rule check right up here where it says rules DRC. And when you click on rules DRC, that comes up. We went in there and we used it to create our design rule check rules. You'll remember this window a little bit right here. We went through and we told it which layers we were using and our clearance. But what we didn't do was we didn't check. And so if you click on check for errors, it will run through and you'll see that it says, oh, it found errors, no vector font. Not a big deal. We're not going to worry about that. That's just referring to the text that we put in there. Ideally, it says no errors at all right in here. But if it says no vector font, it's just being a little bit whiny. So there we go. Now let's see what happens if we had a real error in the drawing. So let's go back to our design and let's move a component. And I'm going to move the diode right here. And oops, bad place to put the diode. You can see that the two nets right here cross. So the electrical signal coming down from this LED would actually go straight back to the battery, and circuit wouldn't work at all. This LED would glow nice and brightly, but nothing else would happen. So let's leave it right there, and let's let the design rule check take a look at this for us. And we'll go design rule check, click on the check button, and now you see one that says overlap. And if you click on there, it will point at the overlap, and it will tell you what layer the overlap is on, and it finds 3 cases of overlap. If you're okay with that, you can clear all those errors and you can go ahead and make that board, but it won't work. So let's do that good old Control-Z function. Maybe I need to click on the board. There we go, Control-Z. We'll put it back over there, and let's do our design rule check again, and check. There we go. One simple error on the no vector font right there. You can see, hey, what do you know? That's what it's talking about, where we have a font. It doesn't like our choice of font. Okay, you now have a board that is ready to print out. Let's turn off any layers that we don't want. And again, come back to design, go into display your layers, and to hide all the layers, we had preset standard turned on. So just come in here, hide all those layers, and then tell it you only want the bottom and the pads showing. Okay, and now you can go ahead and you can type in the print command, and you can print that out on your toner transfer paper or whatever your favorite way of making a printed circuit board is, and you're off to the races. Well done. All right, that's not quite everything. Of course, it's not that easy, but you could make a board right now. Let's turn all of our layers back on. So layer sets, preset standard, and show all those layers. Okay, life's good right there. First thing we want to do is we want to save this file. So again, come up here, file save, and that will save on there, and it checks up in there, and we should transition to V3 in just a moment. There, look at that. Our schematic, okay, we should also make sure that that's saved right in here. Okay, it's looking good, and let's save that. It's still version 3, we haven't changed it. And let's come back to our project right here, and let's save that. Okay, now what's really cool about Fusion 360 with it being a cloud-based package is that you can invite people to your folder by clicking on the people right there. And no, this is me right here, but you can type in somebody else's email address
and invite them to come in, and they can help you edit your file and take a look at your file and help you figure out what's wrong with your file. So from a distance working type of perspective, it's a pretty useful package that way. Okay, and to get back to your data, click on data. But there you go. Circuit board done. You can invite people to take a look at it. Next time out, we'll take a look at a more complex board.